Welcome to another deep dive. Today we're going to be tackling a big one in the world of electricity. We're talking about Ohm's law.
Ah, yes. Ohm's law. It's one of those fundamental concepts that underpins so much of what we understand about circuits and electronics.
And it's a topic that you, our listeners, specifically requested we cover. So we dug into some great sources, like a classic physics textbook, and even Wikipedia's entry on electricity, just to make sure we've got all the angles covered.
Definitely a good idea. It's amazing how much depth there is to a concept that on the surface seems pretty straightforward.
Right, like voltage, current, resistance. Pretty basic stuff, you'd think. But then you start digging into how those things interact and the implications for everything from tiny circuits to massive power grids. And it's like, whoa, there's a lot going on here.
Exactly, and the implications are pretty mind-blowing when you think about it.
So let's break it down, starting with the absolute basics. What is Ohm's law in a nutshell?
Well, think of it this way. Imagine you have a water pipe.
Okay, I'm picturing it.
Voltage is like the water pressure, the force that's pushing the water through the pipe.
Gotcha.
Current is the flow rate of the water. So how much water is actually passing through a point in the pipe per second, for instance.
Okay, makes sense.
And resistance is like the friction inside the pipe, anything that's slowing down that water flow.
So basically, Ohm's law is saying that the more pressure you have, the faster the water flows.
Right.
But the more friction there is, the slower it flows, right?
Exactly. It's all about how those three things relate to each other.
So if we swap out water for electricity, we're talking about voltage being the push behind the electrons, current being the rate at which they're flowing, and resistance being anything that hinders that flow.
You got it. And the equation for Ohm's law expresses that relationship mathematically. It's I equals V over R, I being current, V being voltage, and R being resistance.
So if we increase the voltage, we increase the current.
Mm-hmm.
But if we increase the resistance, the current drops.
Precisely. It's a simple equation, but incredibly powerful when you consider how it applies to everything from a tiny LED to a giant power plant.
I bet. So let's dig a little deeper into each of those components, starting with voltage. You mentioned it's like water pressure, but what is it really in terms of electricity?
Well, at its core, voltage is a difference in electrical potential energy between 2 points in a circuit.
Okay. Electrical potential energy. What does that even mean?
Think of it as the push or force that makes electrons want to move. Electrons are those negatively charged particles that are buzzing around atoms, and they tend to flow from a point of higher potential energy to a point of lower potential energy.
So a higher voltage means a stronger push on those electrons, which results in a higher current.
You got it. It's all about that potential difference.
Okay, that makes sense. Now, what about resistance? We often think of resistance as a bad thing, like something that's getting in the way. But our sources suggest it's actually pretty important, right?
Oh, absolutely. Without resistance, you wouldn't have any control over the flow of electricity. It'd be chaos.
So resistance is like the traffic cop of the electrical world.
Haha, I like that analogy. It's what allows us to direct the flow of current, make sure it's going where it needs to go, and doing what it needs to do.
Okay, that makes sense. And it seems like different materials have different levels of resistance, right?
Exactly. Some materials are much better at conducting electricity than others. Like copper and aluminum are excellent conductors. They have tons of free electrons just hanging out, ready to move.
Like an open highway for electrons.
Yeah, perfect analogy. But then you've got insulators, like rubber or glass. They hold on to their electrons super tight, making it really difficult for current to flow.
So more like a dead-end street for those electrons.
Exactly. And that's why we use conductors for wires and insulators to protect us from getting shocked.
Makes sense. But our sources also mentioned that even insulators conduct a tiny, tiny bit of electricity. How is that possible?
Well, even in insulators, there's a tiny chance that an electron might gain enough energy to break free and move around.
So it's not a completely impenetrable wall? Just a really, really high hurdle for most of those electrons.
Precisely. It's all about probabilities.
Wow. The more we dig into this, the more I realize there's so much more to these seemingly simple concepts.
Oh, yeah. We haven't even gotten into things like resistivity or superconductors yet. There's a whole universe of electrical phenomena waiting to be explored.
Okay, before we get too far ahead of ourselves, we're going to take a quick break. But when we come back, we'll dive even deeper into Ohm's law and all its amazing implications. And we're back, diving deeper into the world of Ohm's law. Before the break, we were talking about conductors and insulators, and it got me thinking, are there any materials that kind of straddle that line between the two?
You're talking about semiconductors, right?
Yeah, semiconductors, they're kind of a big deal, aren't they?
Huge. I mean, they're the foundation of modern electronics.
So how do they work? Like, what makes them different from regular conductors or insulators?
Well, think of it this way. In a conductor, you have lots of free electrons just roaming around, ready to carry current.
Right, like that open highway we talked about.
Exactly. And in an insulator, those electrons are all locked up tight. No easy flow there. But a semiconductor is kind of in between. Its conductivity can be tweaked depending on things like temperature or impurities.
Tweaked? How do you tweak the conductivity of a material?
Well, you can introduce impurities into the semiconductor crystal. This is called doping.
Doping. Like what athletes do to get an edge.
Sort of. But in this case, we're adding specific atoms to the semiconductor to either give it more free electrons or create holes where electrons are missing.
Holes, like empty spaces.
Yep. And both free electrons and those holes can contribute to the flow of current. It's a bit complicated, but the point is we can fine-tune the conductivity of a semiconductor to suit our needs.
That's pretty wild. So by controlling the impurities, we can make the semiconductor more or less conductive.
Exactly. It's like having a volume knob for electricity. And that control is what makes semiconductors so incredibly useful in electronics.
So this is how we get transistors and microchips and all that good stuff.
You got it. Semiconductors are the brains of our digital world.
That's incredible. But let's zoom back out for a second. Remember how we talked about resistance being important for safety? Like with fuses and circuit breakers?
Oh, yeah. Those are classic examples. They literally save lives.
So how does resistance work in those situations?
Well, a fuse or a circuit breaker is designed to have a very specific resistance. When the current gets too high, the resistance causes the fuse to melt or the breaker to trip.
It's like a safety valve, cutting off the flow of electricity before things get out of control.
Exactly. It's resistance doing its job, protecting our circuits and appliances from damage.
I'm starting to see how resistance isn't always a bad thing. It can be pretty useful.
Oh, absolutely. In fact, it's also the key to generating heat in things like electric heaters and toasters.
Oh, yeah. I never thought about that. But it makes sense. The more resistance, the more heat is generated.
Right. That's why those heating elements are made of materials with high resistance. They're designed to get hot.
This deep dive has really changed my perspective on resistance. It's not just about slowing things down. It's about control, safety, and even creating heat when we need it.
It's all about understanding how to work with it, not against it.
And that, my friends, is the beauty of Ohm's law. It gives us the knowledge to harness electricity in amazing ways.
And speaking of amazing, we haven't even touched on superconductors yet.
Oh, yeah, those are like the rock stars of the conductivity world.
Yeah, exactly. But we'll have to save those for another deep dive.
That sounds good to me. We'll be sure to add that to the list of future topics. But for now, we've got to wrap things up.
Time flies when you're having fun with electricity.
It really does. So to all our listeners out there, keep those questions coming. We love exploring these topics with you. And who knows what other electrical mysteries we'll uncover together in the future. Thanks for tuning in. And we're back for the final stretch of our deep dive into Ohm's law.
It's been a fascinating journey, hasn't it?
Absolutely. We've covered so much ground, from the basics of voltage, current, and resistance to the mind-blowing world of semiconductors.
And we've seen how Ohm's law connects it all together.
It's amazing how this one simple equation can unlock so much understanding about how electricity works.
It really is. It's a fundamental principle that governs so many aspects of our world, both natural and man-made.
So before we wrap things up, is there anything else we should touch on? Any final insights or thought-provoking takeaways for our listeners?
Well, I think it's worth emphasizing that Ohm's law isn't just some abstract concept. It's a practical tool that's used every day by engineers and scientists.
Right. We talked about how it's used in circuit design, but I bet there are tons of other applications we didn't even mention.
Oh, absolutely. It's used in everything from medical imaging to telecommunications to renewable energy systems.
Wow, so it's really a cornerstone of modern technology.
It really is. And it's a great example of how understanding basic physics can lead to incredible innovations.
I totally agree. It's like once you grasp these fundamental principles, you start seeing the world in a whole new light.
Exactly. You start to appreciate the interconnectedness of everything.
So true. And that's what makes learning about this stuff so exciting.
Definitely. And I think that's a great note to end on. Always be curious, always keep exploring, and never underestimate the power of a simple equation.
Couldn't have said it better myself. Thanks for joining us on this deep dive into Ohm's law.
It's been my pleasure.
Until next time, keep those brains buzzing.